the night. Have to predict. So we did one hackathon with plastic. I didn't know plastic things. Water, water, ocean, and beyond the water, and we have to take the small 80-90% on the regular. Now I think this year they're doing.
Yeah, this test sampling. The label wanted to identify all the symbol.
Take out. And so outcome. Maybe also something. What is thought? You're not asking whether how would you thought from healing, some what we see the design. I don't know what you're asking. Objects on what's action out to know. They are looking at multiple on our application. Simple applications is built for software 7 to determine your next 5 years. Yeah. Big session.
Hey, all, good morning. So, audible? I usually have a feedback that I have a
Good morning, sir. You are audible.
I'll try to be as loud as possible. If not, you just so yeah, as I think Dr. Shinu gave a little bit more in depth for me. So, but just want to keep expectations realistic. So myself, for you. Slides, we can see that. Maybe I need to change the situation. So I'll tell a little bit of my background. I did my master's in computer vision and machine learning in 2011. Way back, there was not much hype about machine learning. So I started my career as an humble image processing engineer. Probably this is a little bit outdated nowadays. We don't see any more image processing. Almost everybody are using this. And then it got evolved. I started building algorithms by writing handwritten codes and algorithms directly processing the images. Okay. And then later, later it got evolved, right? And last probably 12 years, 10 years after 2012, got evolved a lot. And honestly, even I'm not updated to the latest advancements. It's really hard to keep updated yourself, right? It keeps changing every week. But what is most important is to have a fundamental understanding of this area. Then you can quickly pick up wherever you can. I think you all guys are experts on your own areas. You know your backgrounds will probably get to there. That's how I started as an image processing engineer and then slowly transitioned and stepped into the position I am now. So currently, I am in Vehicle Technologies. It is one of the Baker Hughes listeners, and Baker Hughes previously was General Electric GE. So we got split from GE and we formed Baker Hughes. Baker Hughes is basically an energy technology company, and Vehicle is mostly an inspection technology company. Uh, um, Recently, like months back, I think we might have heard some news that we know that we did. So we will be going out of techniques. And then, so primarily we build industrial inspection solutions, focusing on something called the MDT, non-destructive design. And what we have is we have different modalities: visual, ultrasonic, X-ray, CT scan. And my main focus around 60-70% is on the visual business. So what do you mean by visual is basically they are normal images and videos. And so these boroscopes are used in aerospace inspections. Am I audible? So these are typically used in aerospace inspections. So we have this big aircraft engines that drive these aircraft, aeroplanes, and these engines has to be inspected at a regular interval because they go through a certain wear and tear, and even smallest of smallest anomalies like cracks, leaks can lead to major catastrophic. So this has to be inspected, and these are like very high stake inspections, not just a normal quality inspections that you see it in some surface quality products like that. This has to be even a single defect missed to lead to a big problem. So that is why we are building the most advanced vision techniques for these machines. So earlier, they just have a very manual way of inspecting. They insert the boroscopes and then they see visually whether that's a defect or not. So now we are providing AI assistance to them that in addition to the humans, the AI also sees whatever the human sees, and then they identify the defects automatically and then indicate that to the humans. The humans take decisions whether that is acceptable or not. Here the main reason tool is camera. Yes. And very method. Kind of, yes. Your IoT also is no, so the remote monitoring IoT is on the OEMs who are manufacturing these engines. So the OEMs mainly are the Rolls-Royce and GE. These are the two major aircraft engine manufacturers. We don't have access to the sensors and the IoT data that we are just partner to these GE and Rolls-Royce OEMs. They purchase our horoscope devices and they use that to inspect their business. Okay, I just quickly show you. This doesn't again. This doesn't look like marketing, but if it does look like marketing, you just let me know. I'm just giving you a context. This is how the device looks like. Just giving you because it's more like an applications than
Hello,
the
sir. Your
theoretical,
screen
and
is
it's
not
coming
there.
from my own
Hello.
experience. So this is how the boroscope looks like. And what do we inspect is something like this. Okay. Oh, online.
Hello, sir. Your screen, it's visible now. Thank you.
So this is an internals of an aircraft engines. The aircraft engines are just a series of blades. Right? It revolves at a very high speeds, and they have different regions like hot region, cold region, high pressure turbines, low pressure turbines, low pressure turbines. And then there is a fuel injection area is there. Then there is air is sucked in, it's then compressed, and then it's mixed with the fuel, it's burnt, and that creates an energy thrust which takes the engine forward, sorry, the flame forward, right? So it has series of blades, and these blades are of this much size. 6 centimeter is what's the typical size, but in here it was bigger because of the cameras. And this goes into different defects, right? Because when a foreign particles hits, it can create some indentations, nicks, dents. It can create a crack in the blades. And if you don't notice those cracks at a very early stage, then those cracks propagates, and then the blade gets damaged completely. And you can imagine what would be the implication of it, right? So these are huge things, right? So sometimes what happens is the humans find it. This is very highly controlled inspections. So even if the inspector makes small mistakes, there will be a lot of investigation going on, right? And so they'll be very, very careful. But even then, humans makes mistakes. So that's why the arrows, I mean the AI models come in assistant to them to identify that even in the small things they miss, the AI model could identify. So we also have something called as blade counter, which means everything has a certain number of blades, just like our fans. And previously they count these blades manually, like 1, 2, 3, 4. And now we have an AI model that can count these blades automatically for because they have to ensure if a particular stage of an engine has an expected number of blades, let's say 72 blades, 72 blades has to be there. So they usually count and then say there's 72 blades. And it's little bit time consuming. So they have to just wait for it to rotate and count. Okay, so that's a bit of background about me. We leave a probe. So this is how it looks, right? Ah, yeah, in the probe. It's like a 6 meter probe, which can be inside the maybe the same model is running inside the device, or you're just taking the picture and model analysis is running. It is running on the device. It's running on the device. It is running on the device. So it is in real time we are identifying these defects. And this is also the device has a certain fixed limited compute power. This is not NVIDIA GPUs or any GPUs. So it has a basic Intel processor, which means that we have to optimize the model in such a way that it can run real time in Intel processor. Intel i5. Intel i5. Then we optimize with Yes. Yeah, we in this way we acquire the video, and when we are acquiring the video itself, the model runs on the video real time, then it shows the defects. This is the live mode. We also have a still mode where the user can grab an image and then run the model on it. Okay, so that was a quick background about me. Um, So it's about 60-70%, 70% or 75%. We have a long way to go. We have been developing this for almost 4 years. Yeah, 4 years now. So we don't claim we are 95%, 98%. We also have published our data sheet showing our performance. So we are very transparent because I told you it's a very high controlled environment. You can't just make up numbers. So it's about 70% accurate. So we are continuously improving the model. So it has a lot of issues like false positives and it can miss something like this. So the data is the key. So getting data is a challenge, but recently we have partnership with our OEMs like GE. So you can see some of our press release we done with GE. So these are the JTTAs that we are driving with GEs, and we released that yeah we are developing some AI models. So we acquire data from them because we don't have data. It's only they have the data, they own the data, but they are willing to share the data to us so that we can improve. Anybody can claim any number. They might say 90%, but based on the benchmark field study that we did with our customers, our customers agree that we are the best in class. We also have competitors. They have tested all the models and compared it, and they agree that our model is one of the best. That's basically a ground check. We don't go by numbers. Because numbers you can make it up. Based on a test data set, internally it gives a really high numbers. Okay, but when you do a ground check, the real world scenarios are huge, right? I think it will take another 5 years or probably more to reach that plateau. And the same with LLMs also, right? We used to have this leaderboard where they say we outperformed the previous version. And sometimes what happens, the user test the model, then they say it's a crap. For academic wise, putting up the leaderboard is easy. All the institutes and academic research labs, they just pick up some benchmark data and they can make the model outperform the previous model, and they show that we are the current leader. But the real test is to make sure that it is working on a real world scenario, and the certification has to come from the real user, the customer, and not by the leaderboards. So we focus on that, not by anything else. Yeah.
Let's say we teach on 100% and the movie is 70%. There are chances that 30% of the area is the problem.
Mhm.
So, I need to with customers trust. Did you give any other process to fix everything? Because these kind of problems will accept when you say that it's like a medicine type.
Mhm.
Like, so you are saying the 70%, whatever we have, 30% how you convince them.
So it's
Yeah, I mean, just give me the
yeah,
yeah, there is the engine. We keep the camera and all the photos. We just analyze them. Now there is 70. There are chances that something could be there inside. Like the human goes and put the camera and maybe they can all. So how do you how the customer can how they do some other things?
so currently the adoption rate is pretty low. So they are not trusting these AI models to do the inspection, similar to how doctors, they don't use any AI models now, right? Even though there are a lot of AI models that can do automatic ultrasonic testing. It's same like that. We call it something like we are industrial doctors, right? So and we are also have a human's life instinct. So we are just at a very assistant mode, not in an automated mode. So we just provide them an assistance so that they slowly build that trust, and probably down the line 3, 5 years, we may reach there. Currently, we are not there, but slowly we are getting there. And currently, no regulations allow the AI model to write any report, inspection report. The final call is made by the humans. So the humans has to make sure that he identifies the rest of the 30%.
Humans are there after.
Which is not a normal. But we are, so the difference maybe is, for example, some new generation of inspectors will come, like they have very less experience. For them, it will be because they.
You're being manually away.
Mhm.
Now you are at least getting 7% that is one to be able to understand. I understand that, but then the final reason other kinds of
Yeah, it's the human has to.
they give mostly that they
Yes, yes. So it is running live, right? So at the time, the AI indicates that there is a defect. So now what happens is the human pay attention to that. So sometimes they may miss, but if the AI finds that and then it is flashing, then the human gets seeing that. So the chance of the humans missing a defect is reduced by this supportive assistant by the AI. It is not better, but it is assisting them so that they don't miss any defect, because they also have human fatigue or variations between the humans, and there is a lack of experience. So there is a huge very factors involved in this. So we're trying to assist them so that they don't miss anything. Something is making there in problem. And you might be doing a lot of all your is what we're doing to make what exactly. Currently, the false positive report also. Yeah,
Do that, even has to become a contract.
yeah, we are moving towards that.
It takes different. And I think now we will see them. So far we have done, yeah.
Oh, yeah. Because this one, right, they go to the aircraft is standing in some airport, and they have to take this device, and they don't have a nearby Wi-Fi connectivity. So connecting to a cloud and running model in the cloud is not practical. Unless something evolves in the communication, some sort of satellite communication that you can connect to internet from anywhere reliable connections, then we can go to cloud. But what currently they do is, see, there are different types of inspections they do. One is the regular, they do it on the wing when the aircraft lands. They just open the wings, they go there and then they do inspections. Another is called like our car service center. The aircraft comes to a service center. So there they have a time about 2 days. They do regular service every year once or twice. There they do a lot of videos, like 200, 300 videos, like each like about 5 minutes. Okay. And then what we are proposing is like they can just upload all the videos to the cloud. We'll do the automatic analysis and give them a report. Service center. Yeah, we do regularly training. So our release cycle is about every year, 1 or 2 updates we release. So, so our current version would be somewhere like 5.0. So probably the next release will come in next year. Okay. Maybe I would like to go a round of introduction so that I understand your background a little bit. And also you can tell me what is your experience in computer vision. Um, so that have a better understanding of components. So anybody already have related to computer vision? Or okay. We will start with definition. The recent training of should be I also work for Vegas. Oh, really? Yes, recently joined. You joined immediately. I used I was looking at maybe PTA and Africa. That was
If it's totally different. I diagram it totally and system. How to do it. So I think working in IBM. So the next generation may be automatically going to figure out and how people can stand up. Because it's coming from next target, of course, with the service, it's going to be the data. And if we keep moving cloud, it is that's why I also had taking that how the deep learning happening. So that's a different with how this region and very good. And AI.
Okay. Okay. Right. Okay, so I think except one or two, most of them are new to computer vision. So we'll start with the basics. Just asking ourselves like, what is computer vision? Why do we need computer vision? And how do we apply computer vision to different problems? So computer vision, again, I also want to tell you that in the current, whatever the ChatGPT era, you can get all these information just in a few minutes. You can just go and just type in once computer vision ChatGPT gives you everything. But if you feel that I'm a little bit like the theoretical, just stop and whatever we have an interactive session at the beginning, let's have it in that way so that I can just make it more live than just going through slides. But there will be a little bit of theoretical we can touch upon. But let's keep it more practical. So computer vision is basically it's a field of artificial intelligence. I wouldn't say it's a field of an artificial intelligence. I'm just bringing this term so that it's more relevant to what the program is about. But I feel that computer vision is more of a computer science, probably 10, 15 years back. But now it's turned into more primarily towards an artificial intelligence, which artificial intelligence itself is, I think, is a branch of a computer science. Um, um, so what does this computer vision does? Is basically the main purpose is to extract meaningful informations from visual data. And when I say visual data, it is primarily images and videos. So we all know there is like tons of visual data. Starting from our mobile, we capture a lot of images and videos. That is on a more of an end user or a common man's access to the visual data. But when we come into the industrial domain, we also have a lot of cameras and vision-based sensors that are deployed into the industrial domains, starting from quality inspections. When they manufacture different products, it could be a simple bottles or soaps or chocolates or any food things. Finally, they have to be visually inspected that they meet the quality standards they have set, right? So you could either do it manually, you can just deploy some 100 humans and they can sit next to a conveyor belt where these products are being transferred from one point to another point. And these humans, they pick up the product and they visually check whether there is any defects in that products, like cracks, holes, or missing products, everything. But this human-based inspection is pretty manual. So in order to improve the reliability and accuracy, and also make it more automated and increase the throughput, you deploy cameras. Now, whatever the human sees, the computer or the camera also sees. But the only difference is that we have some automated computer deployed in our brain that we learn through our development from childhood. We learn and see different things day to day. And we learn that, hey, this is a bottle, this is a table, and this is a phone, etc. But computers don't. They just see only numbers. Right? So they rely on some algorithms, some mathematical functions, which is inherently being wired into our brain. But we have to understand how our brain works by seeing all the visual data and translate them into some mathematical functions and algorithms, and then implement into some coding, and then take the visual data such as images and videos and run through these algorithms and get the outputs. The final output is basically some interpretation that what object it is, where it is located, what color it is, what shape it is. Can you identify those objects? Such like that. Right? So, so when I say visual data, it means that whatever the human sees, that is an visual spectrum. So we also have outside of the visual spectrum, like how he is working on an ultrasonic, infrared. Like those are all invisible invisible data, because the humans cannot see ultrasonic data or infrared. It's outside of that visual visible range. Yeah. 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 So LiDAR data are all outside of the visible range, and they have different types of data. They are not typically images, but they can be translated into some information. So different applications in the real world is like autonomous vehicles. Now we have a lot of these ADAS systems installed in some mid-range to high-end cars, where they have this assisted parkings, assisted lane changes, and all those things, right? So those sort of things are basically coming from visual data. So there are cameras installed around your cars, and they acquire those images and videos. And there's a computer within the car, and those computer process these visual data, and they give you some interpretation that, hey, are you going to hit something when you're going to pass, right? So it could be done with sensors also, but it can also be done using some visual data. Right? So then we have in medicals, we have X-rays, MRIs, ultrasound scans, all these things to do some diagnosis. In retails, we have examples like Amazon Go, where you just walk into a supermarket, pick up items that you need, put into your cart, and just walk away, and you are automatically billed. And how does that work? Because the Amazon Go has like hundreds of cameras in the supermarket. They just constantly watch what you are taking and what you are not taking, and they are automatically billed. But there's an interesting use case that Amazon Go was shut down like 6 months back. Where's the problem? See, this is what I was telling you, that we don't want to overhype the AI. So what they were doing is Amazon, like they deployed like hundreds of cameras per store. They were capturing it, and almost 50% of the building was wrong. And there was like, customer complaints, hey, I didn't take this product, why did you build me? So then they have to send this to some customer care center, and then they have to watch the videos manually, whether they picked it or not. I mean, running that customer care center with the thousands and 10,000s of people was, they are making huge loss. So they shut it down. So something like this, although it looks very fancy, sometimes it's not practical. Yeah, sure. Preferably 3D is what is more accurate than 2D. But for some practical reasons, you could still match it with 2D. But if your tolerance is very, very less, then 3D is what uh, so Tesla, they made a very bold decision that they don't use any LiDAR radar data. They just use only typical cameras. But this Google Waymo, they have big LiDAR evolving at the top, right? You see it, right? Yeah. That is basically a LiDAR. So they just project lasers, and then they get the distance and they do a 3D mapping. But there was a very famous claim by Elon Musk that he challenged that the vehicles doesn't need any LiDAR or radar. Why? Because the human doesn't have any LiDAR. We also just have a normal piece, and we are able to drive. So he said if we can do, the computer is.
But we see the visual data integrity.
Yes. That also has 3D. And it has like 8 cameras. From that, if you have 2 cameras, you can build 3D data. From it.
Really from that point, hidden point, like coordinates and which camera can see the radar in leadership.
Mhm.
And there is a black spot, a blind spot, where camera cannot reach. See, like if you take it and where usually radar and glider can reach. But if you can model also, if radar data reflection, you can model it also. The blind spot basically is radar can no can be everything.
Yeah, there are 2 perspectives of it. Hmm. Yes, yes. Yeah, yeah. Not always we need 3D data. Okay, so okay. Okay, so since most of you are sort of pretty new to what this images are, probably we'll spend some time to understand the basic fundamentals of an image. Um, so the image concept has evolved over the years. Earlier, it used to be films, right? And then the films are no more in place. Everything is all digital image. So what we have is a camera, and camera has a sensor. It has a CCD sensor. This CCD sensor captures the light from environment that is reflecting from an object. And this light intensity is then encoded as an image into your camera. Now, what this images is consist of, it's just an 2D grids of pixels. So an image is basically a 2D image, and then it has a matrix of pixels. Right? So it has so many rows and so many columns of pixels. And each pixels represents an intensity of that light that is reflected from the object to the sensor. And the intensity of that light of each pixel ranges in the sensor. It is basically a continuous value, but then when it is then encoded as a digital image, it is quantized and digitized and then normalized to a range of 0 to 255. So 0 is black and 255 is white. Why? Because it is an 8-bit image. So 2 to the power 8 is 256. That's why each pixel has a range of 0 to 56 or 0 to 55. Understood. And whatever the in between values from 0 to 255, they are like more like a grayscale values. So 0 is pure black, 255 is pure white. In between black and white, there is a series of grayscale values. So the image can be represented in different format. So when you are acquiring an image, it is acquired as a color image, and it has three channels: red, green, and green. Um, and these are basically representing the visual range of our human brain. So we see from blue, green, and red, and beyond blue is basically ultraviolet, and beyond red is basically infrared. We don't see those things. We see only between blue and red. And whatever the different millions of colors that is possible within this RGB space, that's what the human can see. It's almost like 16 million colors is what the human eyes can see. Um, RGBW, what is white? Yeah, there are so many, like almost like 40 types of image representations there. Okay. Yeah, as I mentioned, there's like 40 different representations there. Probably that is one of that. And there might be a very specific reason that they are encoding those information into this. But typically RGB is what we do. If there is any special application, probably they do, which mostly we are not using that. And what applications they you are using?
Feelings and data acquisition. That you are traveling from area to or America on to train. Your feelings, you know, like, bring it to the right format. Your exclude bring down we call it the jet lag, right? Jet lag can be enough. So you will not have
That's very interesting.
that.
Mhm. Okay. It's more of a light color space than a like. But then there's one particular color space that image processing engineers work is called an HSV space. It stands for hue, saturation, and value. Uh, this helps to separate the colors from the other two channels and it helps to bring more efficient image processing in the using the color domain. Because what happens in RGB domain, a lot of information overlaps each other, and when you want to separate a certain object from the background, right? So a lot of the colors between the foreground of the object and to the background, there is a lot of overlap will be there. And because of that, getting a good separation of this object from the background will be very difficult or a little bit impossible. But when you move from the RGB space to HSV space, then you separate the colors from the light information. So then all these colors stands separated out. Then separating those objects from the rest of the image will be more easier than working on the RGB space. So these things are very basics. I'm not sure if you will be using this in your applications because now it has totally evolved into a completely different era. But these are some basics that is good to know. So in the right hand side, if you see, right, the top left is what an RGB image looks like. But when you separate these RGB image into its own separate channels, and each channel is basically a grayscale image, and each grayscale image of that particular channel represents that color. For example, the red channel shows you where only those red informations are there. In this, there is only two colors, the red and the white. And if you see the red channels, wherever there is a red, there is red. But in white also, there is a little bit of red. So white is nothing but um, equal mix of red, green, and blue. So white is R, red is equal to 255, green is equal to 255, and blue is equal to 255. So that's why in the white, you will see there is a red. But if you come to the green channel, wherever there is red, it is now black because there is no green in red. But in the white, you still have green is equal to 255. Similarly for the blue. So this gives you a very easy understanding of what does an RGB image representation looks like. It doesn't sit on top of this. The HSV representation will be a little different. The HSV is it's like this. Yeah. So where hue is basically the colors. The hue is red, blue, greens, and they are arranged in a circular manner from 0 to 360-degree. I think 0 is red or something, and then every 10 degrees, like the color changes, right? So then the lightness is basically arranged in the vertical, in the center one, where the top is basically like white and the bottom is black. And then whatever in the side is basically saturation. So the more the brighter, you will have a lot of saturation levels. But if it is completely dark, there is no any saturation level because there is no color at all, right? So that's how this representation is. So then we transform this RGB space into a HSC space. There is a mathematical transformation that has to be applied on to this RGB space to move into an HSV space. And once you move into HSV space, separating red from green, green from blue becomes a lot more easier. You can say that, hey, give me the pixels which are only from 0 to 43 degree. Then that is like red. Give me pixels that are only from 45 to 90. I'm just making up a number, but that will give some blue range. But you cannot do this in RGB space. If we say just give me a red color, there will always be a little bit of blue in that. There will be always a little bit of green in that. So that's the reason. Yeah, yeah. Even in here also we have these colors, right? If we go to color picker, so here this is in RGB mode. So you have it, but you can also change to HSV mode. So L is nothing but V. So here also you can say hue, saturation, and value or luminosity. Hmm. Yep. So they have a HSV value for every. So Pantone is basically a standard, like some ISO standard. For color, they have this Pantone. So it's like common standard for any color. Yeah. So they give a very unique number to each color so that they can communicate the color in the same way across everywhere. Otherwise, if we say light blue is different for you and different for me and different for someone else. But if you say it is Pantone blue 1, 2, 3, it is same across everywhere. That's what you are saying. So basically, when we do segmentations, we typically convert them into grayscale. uh, fish. But it depends on the data. So whether there is a lot of color information is involved or not is what we need to see. But if it is more, we can do the segmentation sufficiently within the grayscale. That's what we start with. So first we convert that RGB image into a grayscale image and we apply segmentation on the grayscale image. There itself we will get some enough separation of what you want to segment from the other regions. But apart from that, if that doesn't help, if there is a lot of color involved in it, then we go for a color based segmentation. So it depends on, we have to see the image first and then we decide. So first always starts with grayscale image to apply the segmentation. If it is not working and if there's a lot of color based things that we can bring in to make the segmentation more accurate, then you go to color based. Grayscale. Mostly we can go with grayscale. We have a good light difference between your foreground and the background. We can mostly do with grayscale. Okay. So typically the image processing pipeline involves like 3 levels of processing. And this is a typical workflow that an image processing algorithm development involves. So it has like a low level, mid level, and a high level. So low level is basically you start with basic image acquisition In the image acquisition itself, you can do a lot of image processing or image enhancements. For example, you could do boosting of the image quality by doing certain image processing like contrast enhancements or the lighting boost. If it is too dark, then you can do something called as HDR, high dynamic range enhancements, where it will take a series of images at different exposure levels. And then when it combines all these images into one, so that it keeps both the high intensity images and also the low darker regions. Because if it is a darker image and if you put a lot of light, then it saturates it, right? It becomes totally white. But if you don't put sufficient light, some of the regions becomes too dark. So what it happens is it tries to capture the different intensity levels at different exposures, and then it combines those images into one image and this gives you HDR image. Even in our mobile, we also have a HDR image, right? But if you take a normal photo and a HDR photo, you'll see that the dynamic range is, so the HDR always have a good range of intensities. It captures both the dark regions and the bright regions better than normal photo. So likewise, you can build in image processing at the image acquisition level itself, at the very low level itself, right? When you're capturing the photo. There is a lot of image processing goes into our mobiles. It has evolved a lot. Previously, it was just a very basic. If you can see the quality of the photo, it has drastically changed over last 10 years, right? So that there is a lot of image enhancements and image transformation is going into the mobile without you even realizing it. There's a lot of things you do after the image capture. Right? For example, if you want to do some effect applied on your photo, you want to make a portrait effect, right? Or if you want to make the uh, photo more vivid, more colorful, or if you want to change the tone of the image, there are different filters of that. Right? So those kind of things happens after this, after acquisition, but even at the low level, at the sensor, you can doing acquisition itself, you can apply a lot of different image processing. Okay. So then let's say once you capture the image, then that's where you start the mid-level processing, where depends on your problem. Let's say if you want to do some food analysis, right? You just have some, uh, let's say rice grains. My first project was on to the rice analysis. That's why I'm just speaking about that. So what we had in that project is that we have to basically determine the broken percentage of the rice. So we know that basmati rice is the most premium rice, and then they have a certain way of determining the quality and the price of the basmati. So if you go and buy the most expensive basmati rice in the supermarket, they have a very low percentage of broken rice. I think India Gate has different sub brands of basmati. And if you buy some 100 rupees basmati rice and if you open it, there will be a lot of broken grains. But if you buy something around 200, 300 rupees, the percentage of broken grains will be very less. Now, what they typically were doing is they go and take some samples using their hands and then they see it and they can tell you that broken percentage is 6%, 8%. They have like about 30 years of experience. Just by looking at that, they will tell you and it will be on spot. Okay, but the industry, they had losing these kind of experienced people, and then there was a lot of need for more automated way. So that's why these image based quality analysis of food was coming in. So what we build a system is that they can just we just put one bag of rice into a sort of a hopper, and then there is a vibrator, and it just vibrates. And then there is a glass sort of a conveyor, glass chute, and the rice falls on it, and then we have a camera built in it, and we have an LED light, and then we captured around 2000 images, and then we process these 2000 images, and then we measure the length of the grains, and then we take an average and start we have some statistical analysis, and then we tell them that hey, the broken percentage is around 6%. And if it is below 6%, it is acceptable. And if it is above 6%, they reject it, something like that. So for this, what I was saying is we acquire images, and after acquiring images, first you need to separate the object from the uh, background. So in this case, the rice grain is the foreground, and whatever the remaining part is the background. So first we have to separate the rice grain from the background, and then we have to measure the length of that grains. We have to identify that it is a rice grain, and we have to measure the length of the grain. And then in this, there is a lot of other additional problems will come, that the rice grains will touch each other. There will be clumps of rice grains. Not all rice grains are separated out. So one rice grain will touch another thing, right? And we have to remove those. So all these things comes under mid-level processing. So we have to identify the object, we have to segment them, we have to then apply some processing to remove the unwanted things and keep only the required rice grains that we are trying to measure. Yeah. Yeah. That's yeah, mid-level. I mean, it, yeah, we can put it in a mid-level. So my first company was called Shortex. So they basically build what you call it. They have a machine called a Shortex, and you just put the rice comes. That will be the last step of your rice processing, and then I process through those conveyors, and then it ejects all those broken grains, dust, stones, everything out automatically, and it happens in real time using this sort of mid-level image processing. So that's why if you go to supermarket, you will see there is something called a Sortex rice, right? So actually, that is not a, there's no rice called Sortex rice. These industrial people, they just use that brand as to make the rice look more premium. Sortex is basically a machine that does this shorting the grains. So they remove all those bad grains out of it. So that's why if you go to I don't know, 20 years, this is what the story they told me. 20 years back, you will see in rice grains, there will be a lot of stones, and our grandmas used to separate it manually, right? So now that is completely eliminated because of these machines. The high level is something like what is running on the autonomous cars, right? So they acquire videos, then they do mid-level processing like edge detection. They detect humans, they detect cars, they detect animals, pedestrians, everything. And then they run like 10 different types of algorithms to identify this mid-level informations, right? And then they put all together into understand the whole scene as a one unified information. And then they have to make decision further upon this. They want to know that, hey, there is a pedestrian crossing my road, I need to stop. And there's two cars behind me, two cars left of me. right? There's a tree inside. All this, everything, they have different models. And they need to do all this mid-level processing. And then they have to combine all these mid-level informations into one high-level scene understanding. Right? Now the humans does this in a fraction of a second, right? Because we are born with it, we have developed that inherent capability. Nobody has to come and teach how to walk or how to understand where things are. This all comes like a nature to us. But for computers, they cannot do it. They have to take all this step by step, acquire low level data, build some on top of that, and take it to a mid-level information like edge detection, all those things, object detection, segmentation, and then put all these mid-level information into a one full scene understanding. Right? Then only they can take further decision whether I should put a brake or should I turn left or should I go straight, all these things. Hmm. If you see the security surveillance or the vehicle monitoring, they just do one specific task. They just monitor, let's say, this vehicle actuated control. Nowadays we have, right, VAC. So they have cameras built in the traffic signals. They just monitor vehicles. They just monitor the vehicle density of it. Right. Based on that, they take some dynamic decision whether I should open the signal or just keep it red for some more time. So earlier it used to be a fixed time, 120 seconds. Whether this vehicle is there or if even the road is completely empty, they just put the red for 120 seconds. But now it is very dynamic. If the road is empty on the other end, they open the opposite end automatically. So they don't wait for another 120 seconds. So they have a very specific task. So they just acquire images, they identify the vehicles, then they do a sort of an density calculation and then they make a decision. But if you take autonomous, they do multiple things at the same time. So that's why it depends on the application. Even for industrial inspections, they do very specific tasks. For them, the mid-level understanding is enough. I know this is an object, and then if there is any scratch or any holes or any anomalies, that's it. That's all I need to know. I don't need to have a full scene understanding of what is going on in my factory.
Maybe it's not everything. It's going very skill and uh, this company. That it means that you push the awareness we have again. Very
Yeah, yeah.
level articulate part of
You're asking whether it will come under.
it.
Yeah, I would still put it as a mid-level unless there are more um, holistic understanding of what is going on into that factory shop floor. I don't think it just detects some smoke and then it raises some alarm, right? It's not making, it's not trying to understand how many people are there. Yeah, so the scene understanding is different, and the mid-level sort of an anomaly detection. More, yeah, it just detects one particular task. It is trying to do one task and it just sends some alarm. So that's why it's mid-level, it focuses on a very specific task. But the high level is understand the overall scene, like how the humans does. Uh, yeah, mostly I think it's manual open CV kind of processing that is sufficient enough. But for example, there is something called super resolution models are there, right? Where we take this low resolution image and they convert that into a high resolution image. Uh, Previously, it cannot be done at the level that current deep learning models of AI models do. Like 5, 10 years back, they were not able to do that. So they can take one low resolution image, like something like 300 cross 400, and even if you try to upscale it to 1000 by 1000, you will see lot of blurrings. But now you can take just a 400 cross 400 image, and you can upscale it to, let's say, 1000 and it looks very sharp. That's what the super resolution you heard of it. So those are all the uh, low level processing. How do I put it? I don't think that comes in a low level processing. That happens after the image is acquired, and then we run some model to improve the resolution and the quality of the image. Kind of follow me? Okay. So even in our boroscope, right? I told you there is a lot of low level processing we do. So we do something called dark boost. We call it dark boost, which means inside the engine, sometimes the light is very low, looks very dark. So then there is something called as dark boost. One button will be there. We just click it, it just makes it brighter. That is low level processing. There is no any machine learning, no AI, nothing. It's pure low level image processing we do. Okay. So time for break. Okay.
You take the quality, let's say, the 3 best